This is the PCAT data analysis video. So we will be looking at ages taken from several publications. Please see the manuscript and a supplementary data file for more information on those data sets. The ages that we're going to be looking at have not been recalibrated for this study, and the analysis presented here is for tutorial purposes only on how to run or use PCAT, and we're not trying to reinterpret data or supersede the published interpretations by previous authors. The TCN ages we're going to be assessing are from single landforms. So we're going to use internal uncertainties in the beginning for generating our probability density estimates, or PDEs. And we'll run through the bandwidth sequentially and examine the various plots for consistency and correctness. So if you would like to follow along, please load the local datasets file, which you'll find in your folder, example local datasets, that should download with the program. To start off, we're going to be looking at Bernard's M2 moraine. It should load up by default. It's the top of the list. And we're on his internal uncertainties. And we're starting with the mean bandwidth. And we're going to hit calculate. It always takes a minute for the program to run the first time. It should be a little bit quicker on subsequent runs. Okay, and then we have our main data figure here, figure 1, and it has the bandwidth located in the title. It's the mean bandwidth. We're going to ignore this for now and just look at our fits. Our diagnostic plot looks good. In the PDE versus model fit, you see that the correlation points align well along the one-to-one line. So that's a pretty good fit. We have a high R-squared value and a good p-value. So let's move on to the next bandwidth and see if we can also converge on a solution there. And we did pretty quickly. All right. So we have the standard deviation interquartile range approach. You see it took a couple of tries here to get to the right solution. And our one-to-one plot looks really good between the model and the probability density estimate based off the cumulative ages. And so let's calculate the last bandwidth. And again, we have a good fit, solved quickly, nice R-squared value, very low p-value, and another good fit in the residual plots. So for this particular data set, PCAT converges on solution with each one of the bandwidth estimators, which is great. That means we have more choices. And there was nothing wrong inherently with any of the plots. Now we can look at these and see which one gives us the best approximation and why. So in subplot 1 across the top, we have our probability density estimate, which is constructed from the summation of the probability distribution of the independent ages. Mean had a very narrow bandwidth, which is why it's so peaky, and you can see here that we basically have a peak for almost every individual sample. So that's a clear indicator that this is way over fit. For an idea of over and under fit, please see the main publication, figure 2. But based off of this, straight away, we can reject this one as being inappropriate. Both the standard deviation and the MAD bandwidths give apparently very similar results. Each of the peaks are labeled. We can move these legends out of the way. And in fact, we see identical peaks, 3.45, 3.45, and 12 and 12. This seems to grab this cluster fairly well, and it looks like it has several ages. So I would look at one of these two bandwidths as the best predictor, and they're basically the same. In a case like this, I would choose whichever estimator gives me the smallest bandwidth. So let's rerun both of those and look at those two numbers. So standard deviation, that gives us a bandwidth of 1.03, and MAD 0.8. So MAD gives us the smaller bandwidth with reasonable clustering. And in this case, since it's young, I would pick the highest probability Gaussian, which would be Gaussian 1. Enter that here. And that propagates our external uncertainties and highlights our preferred Gaussian here in red. And it shows you that these 4 ages really fit nicely underneath that peak. And that seems like a pretty reasonable age for that data set. Okay, move on to the next data set. We're going to look at data from Hendrick et al., 2011. There are 3 moraines, KM1, KM2, and KM3, that are part of a moraine complex. I was present and aided in the collection of the samples, so I've seen the landform. The idea behind the sampling strategy here was to see if we could separate out the distinct moraine ridges that make up the complex. And so we're going to look at each one of these data sets independently, and then at the end I also have them combined, and we're going to take a look at that as well. So let's start off with KM1. Again, it's one landform, so we're on internal uncertainties. Okay, so here we failed to converge. You see that the R-square value is low, 0.87, so it didn't reach that 2 sigma minimum threshold. And here you can see the dispersion between the model, which is the dashed line, and the calculated probability density estimate, which is the red line. No subplot appeared because it failed. So let's move on to standard deviation as a bandwidth. And here we have convergence and a good solution. Nice comparison plot here. And let's try MAD. Again, we have a decent solution. See residuals here, and the pink line is pretty flat, at least in the last run, and good alignment along that 1-to-1 line. So let's look at these two in more detail. From being in the field, we know that this is a semi-arid environment. The moraine complex is in the middle of the valley, and it was clearly an older landform, and you can see that bear out in the plot of the individual ages here. There's lots of landform degradation, exhumation of boulders, and probably surface weathering of boulders as well, skewing these ages young. In a case like this, we want the oldest component Gaussian possible that comprises at least 3 ages. We can see in the MAD that it's very tightly fit to these component Gaussians. It's very peaky. I would say this is overfit for such an old landform with such a wide spread of ages, and would eliminate that one. Based off of the standard deviation IQR bandwidth estimator, we have 3 peaks. They're much broader, but it seems to align better with both the independent ages that you see here and the histogram of age distribution. And I need to actually recalculate that to look at the table, so we'll do that. Gives us the exact same plot. We can see here that Gaussian 2 encompasses at least 5 ages at the 2 sigma range. So that would be my preferred Gaussian. Gaussian 3 only has 1 age. Again, I'll go for the oldest component Gaussian that has 3 ages, or completely encloses 3 ages. In this case, that's number 2. Now, you see it basically grabs everything here. It's sharing probability with its other peak with some of these independent ages. And that's reflected, the spread of those ages are reflected in the uncertainty, right? So 71,000 years plus or minus 30,000 is quite a wide spread. This is also quite a spread out wide data set, so it's difficult to be more accurate than that with so few samples and such a wide spread of ages. So I'm going to stick that off over to the side. Down here, actually. Next, let's look at KM2. Let's start over. The mean bandwidth. Okay, that one converged. Do the the standard deviation. We have a nice residual plot there. Again, nice model to actual data plot. Good fit, good R-square value. And we'll calculate the MAD. And starting with the mean, so that's taking the mean of the independent age uncertainties and using that as a bandwidth. And again, we're way overfit for such a wide spread of ages. You know, each one of these peaks is basically grabbing one or two ages, and you got a little cluster here. But this is way overfit again. You can see how the cumulative PDE basically matches independent ages. So that's not good. So we're going to eliminate that one straight away. Both of these look pretty reasonable. They're both bimodal. The MAD has a bigger dip down in between the two clusters of ages that we see, an older cluster and a younger cluster. Both of those seem fairly reasonable. The model fit plot for the MAD bandwidth, as you can see here, has some divergence in it and kind of a curve shape to it. And you see that show up, just make this big, here between the model and the probability density estimate. The model being the dashed line. You see it's estimated high here and high there. So this fit is not as good as the STD estimator. So based off of that, because we have two very good options here, I would eliminate this one. So then our best model is given by the standard deviation interquartile range bandwidth estimator method. And again, this being an older landform, this is not anywhere near global last glacial maximum ages like under 30,000. We have this nice old cluster out here. I'd say that this Gaussian, component Gaussian 2 would best represent the age of this landform. So I'm going to put a 2. And, oh, that gave me an error, so that was good to show you because the last one I calculated was the MAD, and the MAD plot's no longer here, so it can't do anything with it. So I need to recalculate the standard deviation plot so that the program is referencing this plot specifically. And here we have the age and the external uncertainties as well propagated. And again, it's older age, 88,000 years, and a very large uncertainty, plus or minus 26,000 at 1 sigma. Let's throw that over here on top of KM1. And we'll move on to Moraine 3, KM3, calculate the mean. We have a good model fit plot. So let's calculate the standard deviation. This is decent. It's not perfect. It's completely reasonable. The dispersion is symmetrical around the 1-to-1 line, and it's not very far off. There's no dots being plotted way off here, so that's a pretty decent fit. I'm happy with that. And we'll calculate the MAD. Again, another very nice model fit. So let's look at these three. And what we see here is we have 3 ages with similar uncertainties and 1 age with a wider uncertainty. And here's their density estimates for those individual ages. And again, the cumulative plot basically mimics these 3 tighter independent ages. So basically independently separating out these ages. So this is definitely overfit. And the same goes for the mean bandwidth. It has 3 peaks that also match with those ages. So that is also overfit. That leaves us with the standard deviation, interquartile range, bandwidth estimator. We have 2 Gaussians. It basically grabbed the whole cluster and split it into 2 pieces with some shared probability likely between these middle ages. We're going to recalculate that now so we can see the table. And you can see that Gaussian 2 contains 3 ages. So again, this is older, spread out, large uncertainties, and estimates of sigma, but it's realistic for how scattered this data is. So the oldest component Gaussian that contains 3 ages would be the choice here again, which is Gaussian 2, and we get an age of 86,000 plus or minus 17. So now let's take a look at these 3 plots, and we have moraine 1, moraine 2, and moraine 3, and you could see they're reasonably similar, especially considering the uncertainties, 71,000, 88,000, and 86,000. They each had 20 to 30,000 years of uncertainty, so they're basically all the same age. Now, while I was not a co-author on this thesis or publication, I did talk to them about it, and in their analysis they did combine all the ages to look at that as well. So we're going to do that here and see if we can't do better than these 3 plots, looking at this marine complex independently with such large ages. We're going to follow the same process and calculate the combined data with all 3 bandwidth estimators. Okay, with the mean bandwidth estimator, we did not get a plot. We see that we failed our 2 sigma minimum threshold test for our R-squared value, 0.947. There's a reason that we go after 3 sigma and use 2 sigma as an absolute minimum. You can see the scatter here between the model fit and the probability density estimate. And if we look at the diagnostic plot, you can see that the model went off the rails a little bit up here. But even the best it got was skipping some of these major peaks in here, and you see all the residuals were deviating all over the place. So that failed. Let's move on to standard deviation. Okay, that solved very quickly. Let's return this back to the full distribution so we have a good fit on the second run. And the model fit here, this 1-to-1 plot looks very good. And let's do MAD. Again, we got a nice 1-to-1 plot. Bit more trouble, but it did get there in the end after several runs. So let's take a look at these 2 plots next to each other. So now that we've combined the data from all 3 of the moraines within the complex, there's a lot more distributions to be summed, and in the standard deviation we see we basically have a bimodal distribution and a trimodal distribution in the MAD. I think both of these are acceptable. I prefer the MAD because we see 3 clusters here. We have a cluster of ages here, kind of a cluster of ages here, and then one very old separated obvious outlier. But when we move down, we have good model fits on both, and when this probability density estimate is divided up into component Gaussians, we have 5, so quite a few more for the MAD bandwidth estimator and only 3 for the standard deviation interquartile range estimator. If I was using this one, I would use Gaussian 2, which is 81,000 years. It's effectively the same as the other 3 that we were looking at, 71, 88, and 86. Especially when you take uncertainties into consideration, which were quite large, 20 to 30,000 years. In this particular case, again, a lot of erosion. I see one obvious outlier, lots of exhumed boulders here from landform degradation, most likely, and this kind of middle set. And I would try to pick out the oldest cluster, 3 out of this group, to account for some of that landform degradation and boulder surface erosion. And in the MAD plot, we see the outlier Gaussian 5, 1 age, and in Gaussian 4, we actually do encompass 3 ages. So let's pull that up. Oh, wrong number. We wanted number 4. Delete that one. And we can delete both of these now. So this would be my choice when combining all the data. So when we have more data to look at, we could be a bit more flexible than when we only have a few ages. But essentially, even this is statistically indistinguishable from these other solutions, considering how wide the uncertainties are, because these have uncertainties of 20 to 30,000 years. In the case when we combine all the data, we see we can get much tighter on our certainties, 97 plus or minus 8,000 years. But that's only because we have more data to pull apart. But that would be my preferred interpretation for this overall moraine complex. But I realize that most of the time people don't have so many ages, 12 or 15 ages to analyze, and you can be stuck in these scenarios, but they are still reasonable. As shown, when you combine all the data, you can do a little bit better, but these are not necessarily bad ages. Okay, let's move on to Pratt's 2011 data. This should be a good example of a moderate or more ages that are well clustered. Using the mean bandwidth, again, we see that we have a good solution here in our model fit plot. So let's move on to standard deviation. This is also a pretty reasonable fit. And let's move on to MAD. And this is also another reasonable fit in our model. So let's look at these three plots now. So for the distribution of ages, you see down here in the bottom, we can see that this is a young landform, 12 to 15,000 years old is a spread of ages. There's lots of samples, and they're pretty tightly clustered. The histogram shows a pretty normal distribution of ages, and we see some nice clustering in the center here. And I think that this cumulative density estimate is way overfit for the data that we have. This bandwidth was just too narrow. Trying to separate out 5 component Gaussians from such a narrow age spread, I think, is a bit unreasonable for the resolution of TCN dating. So I think this is definitely overfit on multiple indicators, so we're going to get rid of that. The standard deviation and mean bandwidth estimators both give us very similar results, 12.85, 12.87, 13.74, and 13.68. So I would say that these two results are statistically indistinguishable. In a case like this, again, I would go for whatever bandwidth estimator is the narrowest. So let's recalculate both of those and keep track of that. So for the mean, we have 0.4357, and for the standard deviation, 0.3566. So the standard deviation is in fact narrower. So that would be the plot that I choose. Now, since this is a younger landform, not something that's old and has a lot of exhumation, young tail on it, I would pick the highest probability Gaussian. I would take that approach for anything like around 30,000 years or younger. So in this case, I would pick Gaussian 2, which is the highest probability, as the best age estimate for this landform. And you can see that our external uncertainties is a lot bigger than the age based off the internal uncertainty, the 1 sigma. But that's also still reasonable, although it's large in a plot. If we look here, 13.7 thousand years plus or minus 0.7. That's very narrow. It's a tight estimate, but it is a very good data set. So 1.6 thousand years in the external uncertainty is pretty reasonable. Okay, let's move on to the next data set. And we're going to start over again. Looking at Schaefer's data, starting with the mean bandwidth estimator. So we have a nice model fit here along that 1-to-1 line. So let's calculate the next bandwidth. This is a decent fit. You can see it's symmetrically spread around the 1-to-1 line, so we're not missing any major part of the curve. There's some minor divergence all along this path, but nothing to be too concerned about. You can see it in the diagnostic plot here between the dashed line and the solid red line, which is the cumulative probability density estimate. Dashed line again is the model. There's little bits of offness here and there, but it's very minor, and you can see that also in the R-squared value. Let's calculate the MAD. Again, very minor dispersion, pretty evenly across there. So that's also a reasonable model. Took more iterations to get there, though. So let's look at these 3 plots in detail. So this is a pretty good data set, only 5 samples, so that's a very common data set size. We see one very young age, between 8,000 and 9,000 years, and a cluster of kind of 4. The oldest age has a much wider uncertainty associated with it, and we can see that in a distribution of those individual ages in subplot 2. Now when we look at the model fits, they all seem pretty reasonable. Isolating the younger age and grabbing the cluster as the older cluster is either a single or potentially slightly bimodal. Nothing really wrong with that. We're not pulling out each independent age along the way, so that seems pretty reasonable. When we go down and actually look at the results of these 3, it's pretty incredible. They're all within uncertainty of each other. 11.5, 11.6, and 11.5. The only difference is whether or not we can pull out some of that probability from this older age, which maybe due to its larger uncertainty, or maybe it has a little bit of inheritance. I don't know, I wasn't there. It would be up to the author to interpret their own data, obviously. But from an outsider looking at this, I would go for one of these 2 plots that dice up the probability distribution a little bit better. So I would get rid of the standard deviation and really consider these 2 plots, which are very similar. No real difference between the 2. In a case like this, again, I would go for the one with the smallest bandwidth. We see that the MAD bandwidth is 0.334. So let's see what the mean bandwidth is by recalculating it. It's 0.56. All right, so in this case, I would go with the MAD bandwidth estimator. And I would pick the highest probability Gaussian, of course, because this is a younger landform, which is Gaussian 2. And that would be the age of that preferred Gaussian with the external uncertainties. And it completely encloses these 3 samples. So, a very nice data set there. So now we're going to shift gears a little bit and look at Song's data. We have the Escole data set from his 2007 paper. Lots of ages in these data sets, so we'll be able to have a pretty interesting look at these. This mean plot, straight away, we could see some sinuosity in here. I think that's a bit much divergence from the data set. We can see that it mainly takes place on this lower peak. So maybe it's not such a big deal. We could probably ignore that since it's not occurring high up in the main peak that we're going to want to isolate, because we're really trying to look at the highest probability Gaussian again, because this is young, 5,000 years, 7 to 0,000 years is a data spread. So let's keep calculating the other 2. This is a much nicer fit on the plot here. So that's a better way to go. And with MAD, again, we have a nice model fit, which is minor dispersion. So in light of that, compared to the other 2 plots, I would definitely not consider the mean plot any further, as it was just a little overfit and had that dispersion on the young end that we would like to avoid. With the MAD and the standard deviation bandwidth estimators, we see 3 kind of groupings by eye here of the data, and that's captured well here. This captured in standard deviation as kind of a young tail. Both models fit the probability density estimates well. We have some nice separated out component Gaussians in both, and the highest probability peak is 5,000 5.6 thousand years, basically 5.6 thousand years for both of these. So again, statistically indistinguishable. And as said many times before, I'd go with the one with the narrowest bandwidth in a case like this. We see that MAD is 0.61. Let's see what standard deviation is. 1.643, right? So a much bigger bandwidth. So in this case, I would again go with MAD. As you're starting to see a trend, probably MAD does well as a bandwidth estimator when there are lots of samples present. And the highest probability peak is component Gaussian 3, so I would choose 3. And that's what that plot would look like. 5.6 thousand years, internal uncertainty of 1,000 and external uncertainty of 1.3 thousand. I think that's a pretty reasonable age estimation for this data set. Let's move on to the Mungo stage. Again, we'll start with the mean. Okay, we got R squared of 0.8, so we failed. Lots of dispersion, quite a mess. Looks like we missed a major component here. So that's too bad. Let's look at standard deviation. Okay, that one worked out. We got some dispersion down here along the bottom. Let's see what that's about. Basically, right here, there's one age, right? So we have a nice tight cluster. Age is here, or a couple cluster of ages. And then one very old, obvious outlier that PCAT failed to resolve a component Gaussian for. It's not that big of a deal since it's way away from the main data cluster. We reached our R squared value, so that's kind of the stopping point for the PCAT algorithm to not add any additional component Gaussians, right? So it didn't try to fit that one because it had reached the bulk of the correlation already. So let's try MAD. Okay, and again we have another failure. Lots of dispersion. Looks like we missed the main part of a peak again right here. So not great. Very happy that one estimator was able to solve this. High density of data. You can see there's lots of ages, well over 40. And the bandwidth estimators sometimes struggle when you have a very disparate, separate age like this out. So in fact, I have a copy of this data set with this one very old outlier removed. And so we're going to retry this minus this one age in this data set. So if you have a data set where all three bandwidth estimators fail to converge on the solution, and you have something very, very obvious that you can definitely justify scientifically as not belonging there, which I think we have in this case with this one outlier over here, you can try removing that one age and running the program again. And in this case, you see that this converges in solution, and we have a pretty good model fit here. Let's try it with the standard deviation again. And again, a nice model fit. And that little kick out, which I suspect would be the same. Oh, no, something different in this case. Probably over here, this age right here actually did not fit this very young age. And let's try MAD. Another pretty good, nice model fit along this one-to-one line. So let's look at these three. So again, since this is a younger landform, we're looking at the highest probability component Gaussian. And in the mean estimator, we have 12.885, and the standard deviation, it would be 12.53, right? Grabbing this main cluster. And in MAD, it would be 12.85, right? So pretty identical answers between the mean and the MAD. They all separate out the main probability peak. There's not much difference there, 12.53 to 12.85. And if you look at our original fit that solved, it was 12.54, right? So despite the bandwidth estimator or removing that one very old, very disparate outlier, we're getting the same answers across the board. So this again just becomes a matter of either which model will converge. Sometimes it's only one, and if you get multiples, pick the one that has the smallest bandwidth estimator. I'm not going to bother to recalculate all three of those again to see which one fits. Let's just move on to the next data set, which would be the Skardu data set. And we'll start with mean again. Okay, well, this is surprising. It's rare, but it does happen. We have a good R-squared valued. We met our 2 sigma threshold, and we have a ton of dispersion. Don't like this at all. It's an older data set, as you can see. Very overfit, lots of peaks that match the individual ages, and the dispersion comes in right here, primarily where 2 peaks got lumped together as one in the model. Probably a little dispersion there. Definitely rejecting that bandwidth estimator for this data set. This is a much nicer model fit. We have a good R-squared value, good p-value. So we'll take a look at that one, and let's take a look at MAD. Okay, in MAD we have a nice model fit as well. So let's take a closer look at these two. Wow, it really went through some iterations to get there. Remember that each plot of best fit model after 1,000 optimization iterations, so it went through at least 4,000 runs there. It's pretty interesting. So again, looking at this model, we got this histogram that's relatively normal-ish. There's a very wide range of ages here, 72,000 all the way to more than 150. Was 177,000 years old, 178,000. So almost 100,000 year spread of data that are scattered across here, and I would say that this is very overfit for the skew of this data. This is obviously an older landform with lots of erosion. We also know that geomorphically because it's older than the previous two that we looked at, right? So morphostratigraphically we know it's older. So I would say that this is very overfit and wouldn't consider that any further. And looking at the standard deviation model, this fits a lot better with the data. You have 2 stacked ones over here giving a little bit higher probability, which creates this kind of shoulder on the normal distribution, and then this cluster of young ages. And considering this is an older landform, I would go for the oldest component Gaussian that has at least 3 ages. So let's rerun that. This is standard deviation, so let's rerun it. And then we can look at our age count, and we can see that Gaussian 2 has 4 ages, so it's 76,000 years old, plus or minus 20,000 on the internal uncertainty, 33 on the external, right? So this again is a very spread, large uncertainty data set. But I think that's a pretty reasonable approximation for an old landform like this. So that's going to wrap up our analysis of localized data sets where we look at independent landform ages. I'm the corresponding author, so please contact me if you have questions about your data set, questions about how to use PCAT. I'm happy to look at data sets if you would like or offer any advice. And if you run into any issues, please reach out. Thank you for considering using this program, and have a good day.